Hi, a very good morning. Hope everyone is well and doing great. Thank you for joining Talk Series brought to you by MIMOS Talk. As usual, we bring you exciting new insights into the technologies MIMOS is working on. Today, we'll be looking at video content analysis, traffic analysis in complex scene by our head of complex event analytics, advanced informatics labs, one Zulaikha Kadim. One Zulaikha Kadim is currently a senior staff researcher and head of complex event analysis under Advanced Informatics Lab, MIMOS Berhad. She is responsible for managing a research group in conducting research, algorithm, designing, and prototyping in the domain of computer vision for visual surveillance and traffic analysis. She is also responsible for project collaboration with other university partners in the same area. She has more than 10 years of working experience in MIMOS with the knowledge in developing analytics algorithm to fulfill the demanding challenges in real application. She has successfully filed more than 20 related intellectual properties. Moreover, she has been involved in analytics development and testing and proof of concept projects, as well as commercial projects with external parties. With that brief introduction, let us invite Juan Zulaika to take over this session. Over to you, Juan Zulaika.
Hi, thank you, Lawrence, for your kind introduction. Hi, everyone. Thank you for tuning in. Okay, today I'm representing my team, my research team, in sharing one of our research work, which is related to traffic analytics. So I hope it will benefit all of you. Okay, so content of my presentation today. Okay, I will first explain about video content analysis, the definition and applications. And after that, we will go straight away to traffic analytics, which is focusing on traffic volume count and classification. So what is video content analysis? Okay, this is actually also known as video analytics, which is it's actually a computer program that makes the computer to be able to automatically analyze video captured from cameras to detect and determine any special event in the video itself. So the technology behind any video content analysis or video analytics is called computer vision system. So with computer vision system, actually, we can do a lot of things. So it is actually already benefits in various applications. Okay, for example, in surveillance. So we can see that in previous year, so video analytics actually benefit in surveillance applications. For example, in parameter surveillance, border control, and so on. So in this video, we show some restricted area detection. Okay, not only in surveillance, it also benefit in retail application. For example, in this case, it's actually customer mapping. So the pattern of the customer, how actually they work, they move inside the scene. So it can benefit the retail application. So besides that, we have transportation. Okay, in transportation with computer vision or video analytics analysis, the computer is able to analyze the vehicle in the scene and actually can understand the behavior of the vehicle so that any application related to transportation can be generated. For example, counting or incident detection or any obstacle detection, for example. Okay, in manufacturing, okay, video analytics is also used to inspect products in production line, for example. So where they put the camera and to monitor the products on the conveyor belt. So if any defective product, they will detect automatically and exclude it from the final productions. Okay, in workplace safety. Okay, in this example, we show that video analytics also can be used to detect any in-compliance detection. For example, in this working area, the worker has to wear their PPE or personal protective equipment. So if there's any in compliance, so the system should be able to detect the event automatically. And in agriculture, this is actually drone services. For example, we can use drone to monitor the plantation, to detect or to count number of plants, and also to do some spraying, automatic spraying or pest control. Okay, we can see here actually with the computer, with the intelligence in video analytics, actually we can do a lot of things. It's not only benefit in one sector, it can be used in all the sector. Okay, but for the purpose of today's presentation, I'm going to share with you one of our work related to traffic analytics. So specifically in traffic volume count and classification. Okay, what is traffic volume count and classification? Okay, basically, the purpose of this activity is to know how many number of vehicles, how they move, and what are the classifications of this vehicle for a period of time. Okay, this period of time can be like 15 minutes or even go to 1 hour or even 1 day. Okay, sometimes it is also called as traffic density. So how actually these informations or this data of traffic density is being used, or is it important to have this information? Okay, basically, traffic volume count activity or traffic data survey is actually an essential activity in any traffic engineering works related to design, operation, and also the maintenance. Okay, how they use this information is actually when they want to calculate the level of service for any road service. Okay, because okay, this level of service is actually giving grade to the road system, whether it's having free flow, which is having the grade A until the grade F. They want to know these classifications of the road system. So with this information, actually, they can perform future planning, for example, how they want to plan or how they want to design the traffic facility in future, or they want to understand how actually the road usage currently and how actually the traffic trends. So they can actually predict what is going to happen, for example, in the next 5 years or 10 years. And also this information will give them informations so that they can prioritize how actually they want to improve or how they want to do the road expansion in the future. So this actually, all these level of services actually is calculated or is estimated based on the road performance, which include the traffic density, delay, and also speed. So this is how actually the traffic density is going to be benefit in traffic engineering. Okay, besides that, okay, if there is any company is going to propose any new developments, so they have to also to come out with this traffic impact analysis. So basically this report is actually to understand how actually whether existing or planned road network system adequate to support any traffic any demanding traffic based on the proposed development. So if it is not adequate, so they have to propose any mitigation plan so that the road network system actually sufficient for to support the new proposed development. So with this report, then only the proposed development can be approved or disapproved. So one of the important informations they are going to use to analyze the traffic inside traffic and impact analysis is actually current density. So these are two examples how actually traffic density can be benefit in these two occasions. And for this reason, actually, accurate traffic density estimation is very, very important. So, okay, for that, then we are going to see, okay, in the next slides, we are going to see how actually this traffic analysis is being done in current situation. Okay, for example, this in traffic analysis method, okay, it can be divided into two different parts. One is actually using manual process, and another one is automatic. Okay, when we say manual, actually they are putting people to observe how actually the traffic is having how actually the traffic is. So each people will bring their own tools to monitor how many cars pass through the road, in what directions, maybe some other informations like what class of the vehicles, and also what color and models, for example. So there are some pro and cons for this method. Okay, the pro is actually it doesn't require a lot of budget for simple road network because they can put one people there to monitor the whole road, a stretch of road. But when the road network become complex, for example, maybe more than one lane, and there are a lot of vehicles there, a lot of variety of vehicle class, so they need more people. So in this case, they need more budget to do this manually. So another pro is it can be done anytime. That means without any installation, without any purchasing any hardware, they can just put people, hire people and put there, so they can do the manual counting. So that's why this manual counting is actually very, very popular and is used mostly in previous time. But it also is associated with some disadvantage. Okay, as I mentioned just now, when the road network itself become more complex, so it require more resources to actually put people to count the vehicle manually. So another important issue is related to the safety itself, because the human observer has to be there at the survey area all the time. So in this case, the safety of this observer is actually a concern. Okay, for example, if let's say the survey is to be done for 16 hours per day, so the person has to be there for 16 hours. Okay, so it will actually safety issue will be a concern lah. So another thing is time consuming because the person cannot be leaving the scene while the survey is being done. Okay, and the accuracy also subject to human error. Okay, this is very, very true, whereby when we put human, actually we are constrained by our limitation. For example, we will feel tired, we will feel bored, and so on. So it will eventually affect the accuracy of the manual counting. So for that reason, some actually is go for automatic methods. So this automatic approach can be divided into contact and also contactless. Okay, when we say contact means that the vehicle has to be in contact with the sensor. So this sensor, for example, pneumatic tube, piezoelectric sensor, inductive loop, we require some devices to be installed either on the road or beneath the road. So in this case, the road has to be cut and put the sensor in. So although it can provide automatic counts, that means there is no need to put people there, and it works well with low volume traffic. But it also this sensor is also sensitive to the temperature, and also it can be damaged by road deterioration. And also, if heavy vehicles always go through that road, then it will be damaged as well. So in this case, it will require high maintenance, high cost during the installation, and also high maintenance to make sure that the sensor can work perfectly until the end. Okay, in terms of accuracy, it depends. Okay, this is another disadvantage of the sensor, because the accuracy of the sensor is also dependent on the installation accuracy. So if the person who installed the sensor is not that experts, so if it is actually some misalignment with the sensor angle, for example, it will affect the accuracy. So this is what we don't want. So for that reason, there's another approach which is contactless, and this is more popular now, which is we can use vision-based, which is this vision-based contactless traffic analysis method is what we are going to focus today. But beside vision-based, there are also infrared and radar sensor, whereby this is either active or passive sensor. It doesn't have to be in contact with the vehicle itself. It will monitor the vehicle, but the sensor itself has a limitation. For example, a limited area of monitoring. For example, if let's say we have multiple lanes, right, we might need to install multiple sensor to cover few numbers of lane. Okay, that reason. Okay, in our work, we are actually going for vision-based traffic analysis method, and actually, vision-based traffic analysis method has a lot of advantages as compared to the other two approaches. Okay. So what we mean by vision-based traffic analysis, okay, usually a camera will be put on pole or building beside the road network to monitor the road scene. And this video data will be fed into a video processing engine. This engine can be edge processing, that means it can be at the local locations where the camera is, or it can be also server-based processing. So with this processor or with this engine, we can extract the traffic database or traffic information that can be put into the database, and this information can be used later for visualization for any analysis or any estimations on the road trends. Okay, there are a lot of advantages of vision-based traffic as compared to manual and also contact-based system. For example, besides capturing, for example, in this case, we are going to count the vehicle, right? Beside only capturing number of count of the vehicle, we can also capture a variety of informations. We can, with the camera, actually, we can capture even the license plate, we can capture the color, the models, how actually the vehicle is moving, in what direction. So a lot of information, which is not being given by any of other information, other technique. Okay. Another thing is by having the vision-based traffic analysis, it can perform better observation tasks as compared to human. So because one human can maybe can observe one lane or one type of vehicles, but with one system actually we can monitor all the lanes and all the vehicles at the same time, and it is also more accurate compared to manual and also other sensors. And the algorithm developed for vision-based traffic analysis can always be improved over time because the data is always there, and we can actually train our system to suit the data. Okay, and this system also easier to install, operate, and maintain. The camera actually can be installed permanently or temporarily to capture the traffic data. So it's very easy to install and operate. And for maintenance also, we don't have to, we just have to change the camera in case, for example, there's some maintenance required. And also this system is relatively inexpensive as compared to other sensors that need to be installed on or beneath the road system. Okay, for our discussions, we are going to share one of our case study for traffic volume count and classifications. Okay, the case study actually is done at NPE Highway, Subang Jaya, LDP Highway, Puchong, MRR2, Batu Cave. So if you see here, the camera locations that we put is on the flyover bridge. So the height is more than 4 meters in this case. And we can actually position the camera either we can position the camera either at the side of the flyover or in the middle, so we can have a variety of camera orientation. Okay, this two camera view is actually from the NPE highway. So one camera is looking frontal view, is having frontal view, and another camera is actually looking at the slightly side view of the vehicle, so about 15 degree. Okay, and another two camera is one is from LDP highway and another one from MRR2. So we can consider this road segment is considered as complex environment because based on the traffic volume. Okay, in one research, it says that high traffic volume or low traffic volume is being considered based on average number of vehicles per day on that road. So if let's say average vehicles per day is more than 40,000, then the road is considered as having high traffic volume. While if the number of vehicle per day is less than 13,000, it's considered as having low traffic. So this average traffic per day is actually called as AEDT, or annual average daily traffic. It's a standard measurement for the traffic. So for the 4 use cases that we choose, or 4 cameras that we choose, okay, if you see here, all are actually considered as having high volume traffic because the AADT is more than 40,000. And the highest one is actually the road in LDP highway, which is this one is actually the road near to the IOI mall. So it's very busy road. Okay. So these are some of the challenges that we face or we observe from the data that we have captured. Okay, basically, in all these locations, we capture 24 hours data. So when we monitor the footage, we can see that it have the illumination changes problem, whereby because of the structure beside the road, it will give some shadow effect, as you can see in this video. Okay, besides that, because we want to analyze all the traffic, all types of vehicles on the road. So there is a problem of high variation between the smallest and the biggest object. If you see here, we have motorcycle, and also we have a bus, truck, lorry with 3 or more axles. So if you see here, small and big objects actually will give us problem when we have to represent the object. So the small object is actually having a very little features, but the biggest one we have to have is more features can be represented. So in our classifier later on, we have to be able to capture this variation. Okay, object occlusions. As mentioned earlier, because the AEDT is actually quite high, and we are processing high volume traffic road segment, okay, there are a lot of possibility of having object occlusions. Okay, object occlusion means that vehicles on the road itself is actually merged together with other vehicles from the camera perspective. So if you see here, there are a lot of vehicles side by side. So from the camera perspective or from the system perspective, we are going to have issues when we want to track this object later on. Okay, another thing is weather conditions and also night. Okay, during night, actually less features can be observed from the object itself. So we are actually almost, it's quite hard to actually classify whether this vehicle is correspond to which class of the vehicle. So, and another thing is actually noise from the light beam. So we have to handle this in order to have a 24-hour monitoring on the traffic volume. Okay, next few slides, we are going to share how actually we are approaching this problem and how we come up with our own system. Okay, basically this is an architecture of traffic analytics system. So any system serve ITS services or traffic analytics can be divided into these 4 layers. Okay, the first layer is the lowest layer, which is correspond to image acquisition layer. So at this layer, actually, we use visual sensor to obtain images from traffic scenes. So traffic scenes can be either from the city road or intersections, highway, or even tunnel. So having these informations, okay, next layer is actually dynamic and static attributes attraction. Okay, in this case, actually, from the video that we obtain, we are going to extract what are the vehicle's dynamic and static attributes. So the dynamic attributes is correspond to dynamic characteristic of the vehicle. So this is include the velocity of the vehicles, the directions of the vehicle, and the trajectory of the vehicles. While the static attributes is correspond to static appearance of the objects or of the vehicle. For example, the number plate, the type of the vehicles, the color, the logo, even the class of the vehicle. So all these attributes is not going to change per vehicle. So that's why we call it as static attributes. So under this layer, layer 2, actually this is the main process is being done. So it includes the detection, tracking, and also recognitions. All these are to extract the vehicle's attributes. Okay, with the extracted vehicle attributes, the next layer in behavior understanding, this layer is trying to understand what is the behavior of the vehicles based on these extracted attributes. So with this behavior, when they already understand the vehicle behavior, so only the service can be, or the application layer can be constructed. Okay, these applications can be like electronic toll collections, which require static attributes of the vehicles, for example, license plate, and security monitoring, transportation planning, and route constructions. This one might require the counting behavior and illegal activity anomaly detection and so on. So all these application layer or ITS services actually required information that we gather from the video that we collected from the route segment. Okay, so in the next slides, we are going to share how actually we approach layer 2 and layer 3 based on our use case that we have selected on the 3 routes previously. Okay, okay, what is object detection? So given this raw video captured from the camera, so the objective of detection is actually to detect or to locate objects in the image. So in this case, our object of interest is all the vehicles that pass through the road segment. So the output of object detection is actually bounding box. Okay, bounding box is actually to indicate the locations of the object in the image itself. So from these extracted objects, then only we can do more things. Okay, using more advanced detection algorithm, not only bounding box or locations of object we can obtain from object detection, the algorithm itself also is able to provide us this class level informations. So each of the detected object, not only the locations is available, the location information is available for us to analyze, but also we can know the class level for each of these objects. Okay. Okay, so detection part is very important because this is the first phase. The first phase that this is the first process that should be done in any ITS service development. Sorry. Okay. Okay, if you see here, vehicle detection, actually there are a lot of research has been done for detecting vehicles on the road. Okay.
Puan Zulaikha, we have lost your volume. Can you please check with your...
Okay, so now can you hear me?
Yes,
Okay.
yes.
Okay, so I shall continue. All right. So in when we analyze the system which have been shared in the literature, so vehicle detection in counting traffic volume count, okay, can be divided into classical and deep learning. So classical is further divided into feature-based and motion-based. So what is the difference between feature-based and motion-based? Okay, basically feature-based require only single image in order for them to detect a vehicle in the image itself. So how they do it? Actually, they extract the property of the image itself or the object in the image itself, and they use the classifier on top of it to classify whether there is an object of interest at that locations or not. So, some of the literature is sharing this type of features. For example, HOG, histogram of gradient, highlight features with the Adabus classifier, C features, and so on. While motion-based approach is require multiple images to be analyzed together in order to detect any object in the scene. So the methods include the background subtractions, optical flow to know the flow between current and previous frames, and also even frame difference. Okay, these are all our classical approach how actually people do to detect vehicles in the image. Okay, but more recent approach and more popular now is by using deep learning. So there are a lot of papers actually disclosing how actually they apply deep learning in detecting vehicle for vehicle count and classifications. For example, they use this. So I list down some of these networks that they have used in vehicle volume count and classification. So let's see what is the difference between this motion-based and deep learning. Okay, why I compare only these two? Because motion-based is actually very popular, especially in real applications, not in the academic life, but in the real application, motion-based is much preferable. Okay, because the system itself or the algorithm itself is very fast and also accurate in some control environment. So because of these two reasons, most of real application is still using motion-based algorithm in detecting object in the image. However, this method is actually having a lot of drawbacks, which I will list some of them. Okay, for example, in dynamic background, it will have problem. Okay, as I mentioned just now, motion-based approach will require multiple images to be analyzed together in order to detect the existence of object of interest in the image itself. So it is assumed that the background is totally static. That means when the background is static, whenever there is any pixels with motions, so this pixel will be corresponding to the foreground or our object of interest. But in dynamic background, not only the foreground or object of interest is in motion, but the background itself will be in motion. So this might happen when we have like moving background. For example, we have shaking trees. For example, we have shaking camera, for example. So, or we have shadows. So this will contribute to this problem. So the system or the algorithm itself might confuse whether the motion is because of the object of interest or because of the noise from the background. So another problem is the illumination changes. So when we have illumination changes in our scene, so actually in terms of pixel-wise, the camera or the system or the software will see that these changes might correspond to the object itself. So again, these illumination changes will contribute to noise to the system as well. And another one, okay, we are concerned about moving foreground and also moving background. Actually, we will have, okay, this approach also will have problem if the foreground is not in motion at all. For example, let's say we want to detect any stopped vehicle, for example. So the vehicle will be stopped at the side, for example. So by motion base, we assume that pixel in motion is correspond to the foreground. But in this case, the vehicle itself already stopped. So the foreground itself is not in motion. So it will be absorbed or it will be mistakenly assumed as the background. So in this case, we are going to lose this object. So these are some of the limitations of motion-based approach. Okay, so thank you to deep learning research, because actually deep learning has solved most of this problem. So some of the advantage is actually it provides superior performance in terms of accuracy of detection compared to previous classical approach. It solves most of the problem in classical approach, as I mentioned earlier, and also it provides fast implementation if we are using pre-trained model. Okay, in this case, pre-trained model actually can be directly used because it's already trained with a lot of data. So it's actually already generalized the object representation using the pre-trained model. Okay, however, it still have disadvantage as compared to motion-based approach, which it require more processing power. So we cannot have like real-time application using deep learning algorithm only by using CPU-based low specs, which motion-based approach has no problem with that. Okay, so we need more power, more processing power, the GPU and so on. So the GPU itself with certain specifications, we give different processing time for our system. And also, if let's say we need to train our own model to suit our own applications, so we require to train the model itself using our own data. So when we want to train a deep learning model, so we need a huge of data sets. So to prepare the huge data set, actually it requires a lot of time and a lot of effort. So, and even to prepare a huge data set is another tedious task that has to be done for us to train our own system. Okay, but for the advantages shown by deep learning approach, so in our use case, actually we applying two pre-trained models to our data collected from the three locations just now. So one is SSD network, single shot detection network, which is developed in 2016. If you see here, the pre-trained model is actually already the first 16 layer already trained with a large data set, which is ImageNet data set with more than 1 million data. So it's already, it's actually very, very good, and it can generalize the object features very well. Okay, and then it added a few additional layer, and this additional layer has been also trained with a good data set, a large data set, which is the code detection data sets. So we can say that this SSD pre-trained model is very good because it's already trained with a large data set. Okay, and another network is the YOLO one. Okay, this is slightly larger network compared to SSD. And again, this YOLO also is already trained with ImageNet and also the COCO datasets. So using these two pre-trained models, okay, we try to see which one is better. So we take a sample from the video that we have collected. We categorize as video 1, video 2, video 3. All these three video is having different orientations of the vehicle. So we want to see whether it gives any impact or not. So if we calculate the accuracy, detection accuracy, and also detection rate. Basically, this detection accuracy and detection rate, we use the true positive, false positive, and false negative concept, whereby the true positive is, okay, these are actually comparing or overlapping analysis between the detected object from the system and also the ground truth. So as long as the overlap is more than 50%, which is IOU considered to as 50, so we consider that the object is truly detected, or the TP is considered, and so on. So from this testing, we have seen that the second model, which is the YOLO, is showing consistently better than SSD. And if you see here, actually different orientation give different readings or different accuracy. And the best one is actually video 3, which is correspond to the side view of the vehicle with angle about 45 degree. So, okay, in our opinion, okay, this orientation is much better because with the side view orientation, actually more features of the object can be observed from the object itself as compared to the frontal view and so on. Okay, and this testing we have done on NVIDIA GeForce RTX 2070 using i5 CPU and using TensorRT as the inference engine in C++. So we can see that we can achieve real-time processing for the both detections. And YOLO actually exhibit more processing time as compared to SSD. As I said before, YOLO has a larger network as compared to SSD. Okay, this is some of the samples collected from detections. So for vehicle counting and classification, we apply a region of interest because we don't want to analyze all the road at the same time. So for example, in this case, the ROI is set to be in the forward direction towards the camera. So if you see here, the green one is actually the detected object from the two network. Okay, and from the YOLO itself, we can see that even the objects actually occluded each other, we can still, the network itself can still detect the object itself. Okay, we have done with the detection. So next process is actually to do the tracking. So what is tracking? So given these images, I mean the output from the object detections, I mean the locations of the object detected in the image. So object tracking is actually to locate and keep track of the object in the image over the time. So for example, if we see here, the output of the tracker is actually the tracker level itself, which is number that I showed on top of the vehicles box, and also the trajectory. Okay, what is the trajectory? Okay, if you see here, why actually the tracking is important? Why we do need tracking in our system? Okay, because the tracking will give us the trajectory of the vehicle itself, and this trajectory is the valuable cue in making any decision in any traffic analytics or any other analytics. So and specifically for vehicle count and classifications, we need tracking. Actually, we have to ensure that each vehicle will be counted only once. So that's why we need tracking. So as mentioned earlier, the tracking will give us the trajectory information. So what is the trajectory information? Okay, when the car is actually driving through the scene, so in each image, it will pass through certain point in the image. So the path or the points that the vehicle itself taken in the image is called the trajectory. So basically, the trajectory is the movement of the object in the image. Okay, this is how we solve it. Okay, we are using a classical MOT approach or multi-object tracking approach, whereby we have to compare the active trackers and also the input frame and detection output. From there, we do the motion. We apply the motion model. Basically, this is to predict where actually the previously tracked object might be located in current frame. So we use certain model. In this case, we use Kalman filter with constant velocity because we believe that in a short stretch of road, the movement of the vehicle is not, the velocity could be a constant velocity. So we compare this with the detected object. We do the gating to limit number of observation or number of detected object and the tracker. And then we do the tracker observation associations and assignment and so on. So I'm not gonna explain in details on this approach, but if you're interested, maybe you can email me later. Okay, some of the challenge that we face under tracking. As mentioned earlier, the road that we analyze is actually having a high level of occlusion between the vehicles. So in this case, we are using actually, we are handling the occlusions by having the similarity checking. We are using actually pre-trained CNN model, which is the VGGM. This is very small model, only 3 layers of convolutional layer. So we use that to represent our target object. Okay, so and also we check on the consistency of object label. So when two object, if different class level merge together or occlude to each other, so we check on this label consistency to actually associate which tracker to which object which is inside the occluded object. Okay, then we have the missing observation. Okay, because sometimes detection output not always giving us the detection output in every frame. So we might have missing observation. That means some frame we might miss some detected object. Or even let's say our detection is perfect, we can also apply like we skip frame for processing to ensure that our system can perform real time, especially when we scale up our system one machines to run multiple camera. So we might skip some of the frame. So in this case, some frame we might not see any observation. So we might have the problem of missing observation. So in this case, the tracker will confuse whether this object is still there or the object is already moved out from the scene. So in this case, if the object is still within the active region of interest of our process, we are going to introduce some virtual observations so that the tracking can be done smoothly. Okay, another problem is fragmented observation because usually the large vehicle will occupy most of the image area. So in this case, sometimes one big lorry, it will have more than one detection. From the head itself, it detected as lorry. From the tail also, it can be detected as another object. So in this case, this fragmented observation should be grouped together as one tracker. That means this is correspond to one object. So this is also actually is being handled with our tracking, and also re-identification within ROI. Okay, this is actually similar to the missing observation. That means within the ROI, for example, let's say the object appear within the ROI for 10 times. So maybe the first five times the object detected, and the next six frame and so on, the object is missing. So and after that, it reappear again. So the problem is whether the tracker need to identify whether this object is actually a new object or new vehicles which just appear in the scene, or is actually existing vehicle. So this is what we mean by re-identification within the ROI. Okay, this is sample tracking output. Okay, the points there is actually showing the trajectory of the vehicle itself, and green and red is actually to show that green is when detections giving us the output, and red is actually when we have the missing observation. In this case, the missing observation is not because of the failure of detection, but it's actually because we skip some frame for saving our processor. Okay, next, after we have detect the object and we have tracked the object, we also perform these static attribute extractions, which is we want to know the vehicle class. Okay, so these vehicle classifications, each of the vehicle can be categorized into either one of the 6 vehicle category. So we call it as C1, which is including motorcycle, taxi, and small MPVs. We have also C2, small van, big MPV, and utility. C3, lorry and large van for 2 axles, lorries with 3 axles and above, buses and motorcycles. So if you see here, the category that is provided actually have posed some challenges to the system itself. So one is the low intra-class similarity. Okay, what we mean by low intra-class similarity is something like it's in the same family, but they look differently. So if you see here from the example given, this is a family of C4. And if you see here, vehicles and from C4 can be either lorry, a big lorry, apa tu, bajak and so on lah. So they look differently, even though they are from the same family. But in interclass similarity, that means a different family, but they have a similar appearance. For example, from C1 and C2, because C1 will include small MPV, C2 is big MPV. But in the image itself, all is actually look the same. And even if, let's say, we use the same models, which will resize each of this crop object, so it will look the same, either to have a small MPV or big MPV. So these are some of the challenges posed in vehicle classification. So our approach actually, we are leveraging output from multiple network. Okay, we have trained our own network, which is Inceptions. So we also use the network output network from YOLO V3, and we do some fusions with this, and also we have do some smoothing with the tracker itself before we come up with the final label. Okay, after that, Okay, and this is the last one, which is the vehicle behavior understanding. That means after we get all the vehicle attributes, the dynamic and also the static attributes, we are going to understand how this vehicle behavior. So specifically is to cater traffic volume count and classifications. So to perform counting, we use a virtual line. So whereby we monitor the movement of the vehicle, the track movement of the vehicle. So from before the line and after the line. So to trigger the counter to update. So in this case, we test with our data collected from the 3 locations using these 4 cameras. So total number of clips for testing is 39. Total duration is more than 9 hours. And total vehicle for this 9 hours data is 58,354. So this is the accuracy of counting. And this is the accuracy for counting with classification. So what is the difference between the counting and counting with classification? Okay, basically both are actually to count number of vehicles within a period of time. So in this case, our processing time is actually 50 minutes. So every 50 minutes, there's a ground truth in which give us how many number of vehicles actually pass through the route within this 50 minutes. So we are going to compare the system output and the ground truth to compute the error in calculations. So from there, actually, we come up with the counting accuracy. So for counting accuracy, actually, we don't care what are the class of the vehicles within these 50 minutes. We only care about the final count. So this is the results that we have. For average counting accuracy, for all 58,354 vehicles is 94.53%. So if you see here, okay, the lowest counting accuracy actually correspond to camera view number 3. Okay, this is really camera view which correspond to the Puchong area, which is the LDP, which have the 5 lanes of the road and actually having the highest AEDT, because this road is the most busiest as compared to the other 3 road. And it is consistent with the accuracy of counting with classifications. Okay, and for counting with classification, okay, this one we will consider what is the class of the vehicle itself that contribute to the total counting. So to count this accuracy, actually we calculate the weighted average of counting per each class. Okay, so that means to come up with these results, we count each class accuracy and we get the average accuracy for all to come up with the final average accuracy of counting classification. So for all this clip, the average is 91.5%. So if you see here again, camera 3 or the camera which correspond to the LDP area just now give us the smallest or the lowest accuracy. So if you see here, okay, this is camera 1, which gives us the best accuracy. If you see here, from this view, we can see that the occlusion is very minor. Okay, from this view, the occlusion is very minor. So that's why it can actually perform tracking better and counting better. So this is the camera 3 with the lowest accuracy. Because the occlusion rate here is quite high. So that's the reasons why the system actually has more problem with this view. Okay, so as a summary of my presentation today, okay, this is what we have discussed today. So I have presented a vision-based system to do traffic volume count and classification. So in doing that, we have explored 2 layers of processing, which is dynamic and static attributes extractions, which is to extract the dynamic and static properties of the vehicle itself on the road. So to do this, it involves these 3 processes: detection, tracking, and also classifications. And with these extracted properties or attributes, we further go into behavior understanding, which is to do the counting itself. So using this layer architecture, we can actually construct our system. And this system has been tested or in our use case, which is the camera put in NPE highway, LDP highway, MR2, with this 4 different camera view with different average vehicles per day. Total duration is more than 9 hours. Total vehicles is 50,354. And we can see that average counting accuracy achieved at 97.53%. Average accuracy of counting with classification is achieved at 91.5%. So, okay, that's all. Okay, having said that, Okay, even the system actually has already tested, but we are not testing it for the whole series of data that we have collected. So in the future, we are going to expand the work. We actually currently is doing the junction counting itself as well. So for junction, it is a special case where the direction itself, whether it's moving to the second exit or third exit or fourth exit, the starting and the end of the vehicle movement is important. And also we are handling night scenario and also different weather scenario. So that is our future work related to this traffic vehicle counting and classification. Okay, I think that's all from me. Augments how we dimension as part of the product development method. Okay. All right. Okay. Okay. I think that's all for my presentation today. So back to Lawrence.
All right. Thank you, Puan Zulaikha, on a very interesting, detailed explanation on video content analysis, traffic analytics, a complex scene. We hope you have benefited from this session. We have many more interesting talks coming up. Please do follow us on our social media platform. Just search for MIMOS Malaysia. May also send an email to info@mimos.my should you require more information. With that, we thank you for joining our session and please take care of yourself. Stay safe. Bye bye. And kita jaga kita. Thank you, Ponzalaika.